Assalamualaikum. Today I am going to illustrate the usage of SAP2000 using a very simple beam example. So first, let's see our example. Okay, this is our beam A, B, C, D, fixed at A, roller supported at C and D. Right, you have a triangular load and also moments. E and I are given. E is given as only 8 gigapascal and I is 5.9, 10 to the power of 9 millimeter fourth. Okay, so first let's look at our SAP. Okay, when we open our SAP, this is what will come out. Okay, first before you start, make sure that your unit, you change it to the relevant unit interested, which is kilonewton meter. Okay, and then you click on this button, which is your new model, and then this window will pop up. Okay, again check the unit, kilonewton meter. And then you have some options for templates where you can either take grid only, beam, 2D truss or frames. Okay, for your level I would not suggest you to do 3D analysis. Okay, so for our case it's beam, so you can click on beam. And then let's choose custom grid spacing. Okay, because our spacing of our beam is not constant, it's different. Okay, and then click edit grid. Okay, and then they will give you some grids. So I will always like our origin at A to be coordinate 0. Right, so make this as 0. Okay, B, it's 6 meters away. Okay, this is coordinate. C is 10. And then you have another point, which is point D, it's 20 meters. Okay, you can take a look at the beam just now. Okay, and then click OK. Right, this is our coordinate system. And then restrain, it doesn't matter, we will change the support later. And then beam, take the default value and then click OK. Alright, so this will come out. This is it's actually showing you the same beam but different views. So just let's close this XZ plane first and then look at it in 3D. Okay, this is your 3D view. Okay, you look here, it's 3D view. Alright, so here you have the axis that we are talking about, X, Y and Z. Okay, this is called global axis. Okay, in SAP, okay, let me just show you this. This is the global coordinate system, which explain the global coordinate of the whole structure system. Okay, so in SAP they use X, Y and Z using the right hand rule. Okay, X is horizontal, Z is the vertical coordinate, and Y is the out of plane. Okay, so if your beam I-beam is here in this direction, okay, so this beam will lie in XZ plane. XZ plane. Okay, Y plane is our out of plane, means it is outside this screen. Okay, it's pointing outside of the screen, or inside in this case. Okay, so this is our global coordinate system just now, X, Z. Okay, so if you want to see this beam in a 2D format, you go click on XZ here, XZ view. So this is the view of your structure within the XZ plane. Okay, next let's change the support system. Okay, you know at A you have fixed. So you click on this point, you assign, it's a join, and then change the restraint. Okay, you know it's fixed, so you just at the first restraint bottom here, you just click on fix. Okay, so meaning that your structure cannot translate or move in horizontal, vertical, or any direction, and then rotate in any direction also, and then click OK. This is the symbol for fixed end. Okay, at B, you know that B doesn't have any restraint or support, so you go to assign, join, restraint. Okay, and then you make it free. Free is this button. Okay, so all of the translation and rotation are allowed to move, and I click OK. So the restraint now has gone, and let's see. Okay, sorry, yeah. Okay, at C and D, you know that it's a roller, so you go to assign, join restraint. Okay, you just click on this first restraint, this roller. Okay, you will see that the translation in tree is ticked, means it cannot move in Z direction. Okay, and I click OK. Okay, so this is symbol for roller. Okay, you can always try at the restraint. Alright. Okay, once you have done that, you need to then define the material and then define the sectional properties. So you go to define, you go to material first. Okay. Alright, so for the material, ours is 28 gigapascal. I would assume it's actually concrete, but even so, you can go to add new material here, click, okay, and then you can choose your material type. So let's choose our material to be concrete. Okay, so concrete, change the material name to concrete. Okay, you can change it to any name that you want. And then the most important thing is our modulus of elasticity. Okay, ours is 28 gigapascal, so it's actually 28 times e to the power of 6 kilo pascal, meaning kilonewton per meter square. Okay, plus, okay, and then all other values, if you know, then you can just put it in. Okay, however, most of all of them are not very important because ours is a 2D and it's elastic analysis. These values will become important if it's inelastic. Okay, ours, we are just interested in modulus of elasticity. In addition to that, I would like to inform you about this weight and mass. Okay, in structural analysis, as you have seen in many examples, when we calculate the bending moment, the shear force reactions, we usually neglect the self-weight of the structure. Okay, so if you want to neglect the self-weight of the structure, you don't want to calculate, you need to put this value as 0. Okay, means you are asking SAP not to calculate this weight. Okay, if you want to calculate, you just put a value in. Okay, and then you click OK. Alright, this is our new material. And then you need to define the member. Okay, so you go to define, section property, and then click frame section. Okay, frame section for beams, for columns, for trusses, okay, they use the term called frame. Okay, so beams, trusses, columns are all called frame. So that's why we choose frame just now. Okay, again, define, section property, you go to frame section. We are going to give the sectional property to the your beam. Okay, so if you know a particular section, okay, you can just click add new property. Okay, if it's steel, okay, for example here you can just click on the steel section. For example, in your project you have I section, so you just click and then you put in all the values. It gives you thickness, the width of the bottom flange and everything. Okay, and then if you look at this diagram, you can see that there's a new axis, number 2 and number 3. This is called local axis. Okay, so you have another axis that you need to consider, okay, apart from global axis, and it's called local axis. So local axis is the axis within the member. Okay, it is different from your global. So for beams, the local axis number 1 is within the beam length. Okay, local axis 2 is in Z axis, and local axis number 3 is in out of plane. Okay, so for beams, axis number 1 is your x-axis, axis number 2 is your z-axis, and the third one is the out of plane. Okay, for columns later, if you are interested, if you are going to analyze column later, okay, so if this is your column, okay, column is a vertical member kan? So axis number 1 is along the length, okay, axis number 2 is again within the plane, so this is number 2. Sorry, I cannot understand why. Okay, so this axis, okay, axis number 2 is this one, okay, and axis number 3 is the out of plane. So 3 is always out of plane. Okay, this is for columns. So columns is a little bit different. 2 is your x, 1 is your z. Okay, so axis 1 is always within the longitudinal length of the beam. So this is called local axis. Okay, so in SAP, this 2 and 3 is the local axis. So 3 is the bending. If you want to put in the moment of inertia, okay, moment of inertia, you have axis 3 and axis 2. So 2 is the weaker axis, 3 is the stronger axis. Okay. Okay. In our case, we are not given any sectional property. So what we can do is you add a new property. Instead of you don't know whether it's concrete or not, so just click other, this button, and then choose a general section. Okay, this is what happens when you don't have any sectional property. And since we are only interested in a 2D structure, we don't really need cross-sectional area or actual values, because ours is only bending mostly, so we can neglect it and only input the moment of inertia about axis number 3. This is a strong axis, the bending axis. So ours moment of inertia is 5.8 times 10 to the power of negative 3 meter fourth, so 0.1258, okay, 0.0058, right? And then click OK. Alright, so this is your sectional property. You don't need to worry about the dimension so much. They just put in some arbitrary number lah. Okay, and your material, change it to the new material that we have defined just now, which is concrete. And then change the section name. So let's call it beam 1.0i. Okay, so the only thing that we change is the moment of inertia about the strong axis, axis number 3. Okay, axis number 3 is a strong axis. Okay, other than that, please change the material also, and then click OK. And also remember that for your problem, you have a section of the member that have a higher moment of inertia, 1.5i. So what you can do is just copy this. So add copy of property, change the name to beam 1.5i. Okay, material is concrete. The only thing that changes is your moment of inertia. The moment of inertia is increased by 1.5 factor, so it will become 8.7. Right, and then click OK. Okay, so you have 2 sections, and then click OK. Now you need to assign the frame section just now to your beam. So just click on the section that you wanted. So AB, you know that it's 1.5i, so you go to assign frame, click frame section. Ours is 1.5i, and then click OK. And then for the remaining, you assign frame section, and then 1.0i. So you can read what are the sections that you have already given. Right, next is to assign the load. So first you click on the beam that you are talking about. Okay, you have a triangular load, so you go to assign. This is a frame, so it's a frame load. Okay, it's a distributed load. Okay, triangular. So don't worry about load pattern, you just give it as a default value. The direction is gravity, means it's negative z direction. Okay, at x equals to 0, which is here at A, the load is 30 kilonewton per meter. So you just click 30. Okay, and then at 1, at the end here, it's 0. Okay, and then in the middle, you need to put some values in. So this is relative distance, 0.25. Okay, you can calculate it yourself. It is 22.5, and at 0.75, it's 7.5. Okay, you need to calculate yourself. So this is the relative distance, and then click OK. So this is a triangular load, just as shown in your problem just now. Okay, next you have a load at B, so you click on point B. Okay, there's an X mark here, and then you assign. Now it's a joint, so assign joint load force. Okay, and then the loads are in global axis. Okay, so ours is global Z, so Z is upwards, the force is downwards, so you give a value of negative 200. Okay, the unit is kilonewton. Okay, click OK. Okay, and then at C you have a moment, so click on C. Okay, assign joint load. Okay, and then forces, and then you apply a moment. So you don't have any force in global Z, so make it 0. Okay, and then at joint C you have a moment. So moment, which axis? It's in the out of plane, so X, Z, your moment is out of plane in Y, this one. Okay, use your right hand rule. Okay, so Y moment in Y direction causes a positive clockwise moment of 90 kilonewton meter, and then click OK. You cannot see it because it is out of plane, so you click 3D and you can see that there's an arrow going in Y direction. Okay, that arrow is actually moment. I think it's two-headed arrow. It's a moment lah. Okay, 90 kilonewton meter. Okay, and then XC, and then there's also another load at the middle of this span. So what I would suggest you to do is to break the span into 2. Okay, if you want to read the displacement at that point, you break it into 2. So how to break it? You go to edit, you highlight the frame that you wanted. Okay, and then edit line, and then divide the frame. Click divide frame. Okay, so you want to divide this frame into 2, and then the last to first length ratio is 1, means you are going to break it equal length. Okay, and then click OK. Alright, so now there's actually 2 beams connected by a joint. If you are interested to know what are the beams, you go to display, miscellaneous assignment, and then go to frame. Right, where is it? Okay, and then you can go to frame section. Okay, you can see that you have 1 frame, 2, 3, and 4 different frames. Alright, so then you assign the load at this joint. Okay, so you click on this joint, and then you go to assign joint load, just like just now, and then you assign a global Z, okay, of negative 150. Okay, this is the load negative 150 in negative Z direction, and then click OK. Right, if you want to see the forces, display load assignment joint, and then click OK. They will give you all the loads on the joint, and then if you want to look at the load on the frame, you go to display load assignment frame, and then click on OK. So the one in yellow is the load on the frame, the one in green is the load on the joint. Okay, so that is the loads